Hello everyone, thank you for having your time. I'm honored to give a presentation at this IntelliSys conference. The paper I'm going to present today is called Zero-Shot Visual Emotion Recognition by Exploiting BERT. So the sections are as follows. So zero-shot learning was first introduced due to the issues of traditional supervised learning. This learning process is similar to humans learning to recognize about objects. Suppose a mom wants to teach her baby about the concept of a tiger, then she's gonna show the baby a number of images of tigers and tell her baby that this is a tiger by pointing to each image. So this is how the supervised learning works like. However, they have the following problem that it works only in the closed world. That is, the baby can only understand the concepts that the baby has learned from images. And to learn a new concept, the baby has to go through the same learning process as earlier, which is time consuming. And to collect the samples for new concepts such as dogs and cats, it is labor intensive. And usually for a model to show a reasonable performance, it requires from hundreds to thousands of training images, and it arises large memory occupation. So as a solution, zero-shot learning aims to predict novel classes not included in the training set without retraining. It works like transferring the knowledge. So suppose you want to teach the baby about the concept of a puppy, then you can tell the baby that a puppy is a small dog, and given an image of a puppy, the baby can recognize it as a puppy by understanding the context of the puppy that it is a small dog, even though he has never seen it earlier. So in my research, I used the zero-shot learning for visual sentiment analysis. And visual sentiment analysis aims to predict the sentiments solely from the visual content without any context. So why do we need this? Let's look at the figure on the right. You can see a tweet and Obama hugging his wife. However, the tweet itself does not give much information because the text is too short. But the key clues of sentiments are mainly conveyed through their visual contents. So this motivated the study of visual sentiment analysis. And there are two emotion theories. First is the discrete, second is the core effect or constructionist theory. The discrete theory tries to separate the emotions into a number of categories such as anger, fear, sadness, joy, disgust, and surprise, and it is called the 6 basic emotions. And the second approach tries to frame emotions on an n-dimensional scale. The emotion is represented as a product of two separate neural systems which are valence and arousal. So for the motivation, regarding the discrete view of emotion theory, the basic 6 emotions branch into further classes due to the development of psychological theories. For example, Michaelis' wheel introduces 8 emotion classes, and we aim to recognize those unseen emotions not included in the 6 basic emotions without retraining. And there are 2 ways for zero-shot learning. The first one is explicit, and the second one is implicit. And for the implicit method, the model is trained with unsupervised learning, through which the language models can predict the context of words, and we take this method to predict unseen emotions. And it works as follows. Suppose you want to find the emotion closest to not happy, and among the 3 emotions, and you can guess it as sad because humans can understand the context. So the proposed model is trained by mapping the visual features to the emotional semantic features so that they can find the common space between these 2 latent spaces. And these are the data sets I used. And my question was this: can a visual classifier can better find the discriminative spaces solely by a superior language model over other tasks? And for the data statistics, I use emotion 6 for training data that has 6 basic emotions, and for the test data, I use the art photo which has 8 emotion classes. And the proposed model aims to dynamically recognize the 4 unseen emotions: amusement, contentment, excitement, or unknown during training time. So for the prediction, the formula is as follows, and the predicted emotion has the minimum equilibrium distance with the visual features among the candidate semantic vectors. And looking at the table, it shows the experimental results, and the proposed model shows higher performance compared to the other model that use inferior language model, both in accuracy and F1 score. And below shows the distribution of the predicted emotional semantic vectors using PCA on 2-dimensional coordinates. The left figure shows that the predicted emotional semantic features from the proposed model cluster. On the other hand, the other model on the right shows rather mixed distribution. So for the conclusion, through the experiment, we found that the improvement of language models can help better find the discriminative space of unseen emotions. And this research is expected to contribute to the applications such as automatic tagging system of social media, where the elicited human emotions from images may be redefined. And up to here, this is all for my today's presentation, and if you've got any questions, I'm happy to answer them. Thanks for listening.